The first energization of transmission lines, power transformers, and substation equipment is one of the most critical stages in the commissioning process of any electrical power system. Before newly installed or refurbished equipment is placed into full service, it must undergo a controlled energization period commonly known as soaking, voltage soaking, or pre-energization soaking. This procedure involves applying voltage to the equipment for an extended period under carefully monitored conditions to verify insulation integrity, stabilize electrical components, and identify any hidden defects that could lead to premature failure. Although often overlooked by non-specialists, soaking is a fundamental engineering practice that contributes significantly to the reliability, safety, and long-term performance of high-voltage assets. The purpose of soaking is not simply to energize equipment before placing it into operation. Rather, it serves as a controlled validation process that allows engineers to observe how the insulation system and associated components behave under electrical stress. During manufacturing, transportation, storage, installation, and construction activities, equipment may be exposed to mechanical shocks, moisture ingress, contamination, or environmental conditions that can negatively affect insulation performance. While factory acceptance tests and routine commissioning tests provide valuable information, they may not reveal every defect or weakness that exists within the equipment. The soaking process provides an additional layer of assurance by exposing the equipment to sustained electrical stress before it is connected to the full power system and subjected to operational loading conditions. For transmission lines, soaking generally involves energizing the line at a reduced voltage level prior to full integration into the network. The applied voltage may range from approximately 10 to 30% of the rated system voltage, depending on project requirements, equipment specifications, and utility procedures. During this period, engineers closely monitor insulation performance, leakage currents, and any abnormal discharge activity. This gradual application of voltage allows electrical stresses to be distributed progressively across insulators, conductors, cable terminations, and associated equipment. If hidden defects are present, they are more likely to be detected under controlled conditions rather than during normal operation when failures can have severe consequences for equipment and system stability. Transformer soaking follows a similar principle but is specifically focused on the transformer insulation system and winding assembly. Newly installed transformers often contain residual moisture within insulation materials despite extensive drying and processing during manufacturing. Moisture is one of the most significant factors affecting dielectric strength and insulation life. During low-voltage energization, the transformer insulation system experiences electrical stress that helps reveal weaknesses while allowing the insulation to stabilize. The transformer is typically energized without load during this phase, minimizing thermal stress while enabling careful observation of electrical behavior. This process also allows magnetic circuits and winding structures to settle into normal operating conditions before the transformer is subjected to load currents and full system voltage. One of the most important benefits of soaking is insulation verification. The insulation system represents the primary barrier that prevents electrical breakdown between energized conductors and grounded components. Failure of insulation can result in flashovers, equipment damage, prolonged outages, and significant financial losses. By maintaining voltage on the equipment for an extended period, engineers can identify abnormal leakage currents, partial discharge activity, localized heating, or other indicators of insulation deterioration. Defects that may remain undetected during short-duration tests often become evident during prolonged soaking because insulation weaknesses tend to manifest when exposed to continuous electrical stress. Another important objective of soaking is surface conditioning. Outdoor substation equipment and transmission line components are frequently exposed to environmental contaminants such as dust, salt deposits, industrial pollution, moisture, and airborne particles. These contaminants can accumulate on insulator surfaces during transportation, storage, and installation. When voltage is applied gradually during soaking, minor surface contamination may be removed or neutralized through controlled electrical activity. This conditioning process reduces the likelihood of flashovers and improves the overall dielectric performance of external insulation systems. In regions with high humidity, coastal environments, or industrial pollution, surface conditioning becomes particularly valuable because contamination can significantly reduce insulation strength. Gradual energization also reduces the risk of dielectric stress shocks. Applying full system voltage instantly to new or refurbished equipment can subject insulation systems to sudden electrical forces that may aggravate existing weaknesses. Controlled soaking allows voltage stress to build progressively, giving insulation materials time to adapt to operating conditions. This approach is especially important for high voltage and extra high voltage installations where insulation systems are subjected to extremely high electric field intensities. By reducing the likelihood of sudden dielectric failure, soaking contributes to safer commissioning and greater equipment reliability. Monitoring activities performed during soaking are equally important as the energization process itself. Engineers continuously observe leakage currents, temperature variations, partial discharge levels, transformer oil parameters, and equipment operating conditions. Any unusual trend may indicate the presence of insulation defects, contamination, loose connections, manufacturing flaws, or installation issues. Modern substations often employ advanced monitoring systems capable of detecting very small changes in equipment behavior. These systems provide valuable diagnostic information that can help engineers identify potential problems before they develop into major failures. Early fault detection significantly reduces maintenance costs and improves operational reliability throughout the equipment lifecycle. Following the completion of soaking, a series of diagnostic tests is typically performed to confirm that the equipment remains in satisfactory condition. For transformers, these tests may include insulation resistance measurements, winding resistance tests, transformer turns ratio verification, impedance measurements, and dielectric assessments. The results are compared with baseline values obtained during factory testing and initial commissioning. Any significant deviation may indicate the presence of developing defects that require further investigation.